Okay, so here are those two graphs together once again. Let's go ahead and make some marks on this graph to help us keep track of what's going on. So what I'm going to do is I am going to mark where the original graph f of x has a peak or a maximum, that's right around -1, and where it has a minimum, right around +1. So these two dotted lines that the arrows point to right now sort of mark off three regions on the original graph f of x. Think of it, region 1 as being to the left of the peak. Think of region 2 as being in the middle between the peak and the valley. And think of region 3 as to the far right. So what we're going to do is we're going to explore each region one at a time to see what's going on. So we're going to start at a point roughly at about -1.5, this dot on the graph. And I'm going to pick a point there and I'm going to draw the tangent line at that particular point. Now, because this function at that particular point is increasing based on the definition we just talked about, we see here that the slope of the tangent line is positive. So remember, the slope of the tangent line is the same thing as the derivative. So if the slope is positive, that means the derivative must be positive. If the derivative is positive at that point, then the graph of the derivative should reflect that fact. So now focus your attention on the derivative graph, f prime of x, which is that parabola. The measurement of the value of a graph is the distance from the x-axis to the point on the graph. In this particular instance, we're looking at the point roughly -1.5. So the value of the derivative can be measured with this distance here. And because that distance is above the x-axis, then the value is positive. So of course, if you were to look at that point on the derivative graph and read it, it's roughly what? -1.5, comma, and the y value is 3. So the derivative value is about 3. What's important here for you to see is that that vertical distance, roughly 3, is exactly equal to the slope of the line that we just drew directly above it. Now notice, in that particular region, no matter what point that you pick, when you draw the tangent line, you're always going to get a positive slope. Now as you move further to the left, those tangent lines are very steep, so the slope values will be very big. And you can actually see that. If you were to go out to, let's say, roughly -2.5, it's a very steep slope. And then if you were to go directly up to the derivative graph, you actually can't see that point. It's so high up because the value of the derivative is relatively large. What's important here is that in that region, again, every point when you draw the tangent line results in a positive slope. So down here in the bottom, we're going to say all of these points in this region to the left, region 1, all have positive slopes associated with them. So therefore, at every point, we say that function is increasing. In calculus terms, we would say in this region, the function is increasing. And that's just another way of saying for every point in that region, the function is increasing, i.e., when you draw a tangent line at any point there, you get a positive slope. Now, remember, that slope changes. So as I get closer and closer to that peak, that tangent line is going to flatten out, and so the value of the derivative is going to get smaller and smaller, which means, now go back to follow the derivative graph, the y value is getting smaller and smaller and headed toward the x-axis. Now let's look at the middle region. The middle region, let's take a look at this point right here, roughly at, well, what is that? That looks like it's about just a little past positive 0.5. When I draw a tangent line here, you can see the function is decreasing at that point, so the derivative is negative. That tells me that the value of the derivative should be negative. And remember, the value of a graph, if it's negative, tells you that that graph should lie below the x-axis. So if you follow that point down until you hit the derivative graph, you end up down here at this point, and now that vertical distance is a measurement of the slope or the derivative at that point. And because that distance is below the x-axis, the value of that graph at that point is negative, and that corresponds to the fact that the derivative is negative. Now, that's region 2. Pick any point in region 2, and you'll notice that when you draw a tangent line, the slope of that tangent line will be negative. Sometimes more negative than others, but still negative. So we say that in that region, all of the derivative values are negative. So we put a bunch of negative signs there to indicate that. And so we say that in that region, region 2, the function is decreasing. Now, focus your attention right now on the point x equals 0. That is the point on the derivative graph where the derivative graph is the smallest. It is the most negative there. So what that's telling you then is that when x is equal to 0, the original function f is decreasing at a rate more quickly than it will than at any other point on the graph. And you can see the derivative right there, it goes through the point 0, 2. That's the steepest negative tangent line that you'll be able to draw on this graph because that's the lowest point on the derivative graph. And of course, we can continue this into region 3, pick a point over on that other side, and you can probably tell just by looking at and inspecting the graph that any point in region 3 to the right of the valley, when you draw a tangent line, that tangent line is going to have a slope that is positive. So if it's positive, then as before, we say the function is increasing in that region and tells you about how the original function is behaving. So if you take the entire bottom portion of this slide now, even if you didn't know what the original graph of the function f of x looked like, if you just had this information, you could probably sketch a general picture of what the function was looking like. You knew that f was going up, it was increasing, then roughly at around -1, it changes, becomes a decreasing function, and then becomes an increasing function. Now, as we'll see in a minute, it's not always true that the function automatically changes from increasing to decreasing or decreasing to increasing, but in this case, that's what happens. So the sign of the derivative tells you what is happening to the derivative, but it also tells you what's happening with the original function. Positive function, or positive derivative, tells you that the original function is increasing, and a negative derivative tells you that the original function is decreasing. So let's continue with this exploration. So now that we've seen a visual picture of how a function and its derivative graphs are related, the next thing we want to do is begin to explore